Hey everybody, so what we're going to start talking about now this upcoming week is how skeletal muscle differs from cardiac muscle, especially in terms of how it contracts. So for example, if we think about everything we saw with skeletal muscle, that drawing on the left, we're going to do a comparison between these two types of muscle, cardiac and skeletal. So what we saw about skeletal muscle is that it can experience tetanus, but what's unique about cardiac muscle is that it cannot do that. And another thing that we're going to see is that skeletal muscle, if I pull it out of your body and disconnect it from all of your nervous system, it is unable to contract. It just stops contracting, which makes sense. If you pull a muscle out of the body, it should just stop contracting. But one thing that's unique about cardiac muscle, which we're going to explain, is that if I pull it out of your chest, disconnect it from your nervous system, somehow it can keep on going. So we're going to learn the physiology of this cardiac muscle and explain things like why does the heart keep beating when we pull it out of your chest. So before we do that, let's just take a quick look at the anatomy of the heart, a very rough anatomy. And specifically, we're going to look at the two different cell types that are in the cardiac muscle, or at least two of the cell types. So if we draw out the atria and the ventricles, we'll see that all along the edges, we have these cells known as contractile cells. Their job is just to serve as force generators in the heart. So they're very much like skeletal muscle fibers. But as you guys might remember from anatomy, we also have this network of cells forming this electrical conduction network throughout the heart. And we're going to call these ones autorhythmic cells. So these are the two different cell types that we're going to focus on and explain how they work and how this helps the heart behave in a very specific way. So if we start comparing these two in terms of what they do, what they look like, we see that contractile cells do have sarcomeres, autorhythmic cells do not. And as a result, contractile cells can generate force, autorhythmic cells cannot. But the most important and unique thing is we're going to see whether or not this cell type or this cell type can generate their own action potential. That is, are they a cell that can start their own action potential without anybody else telling them to? And the key defining feature, other than the fact that contractile cells do have sarcomeres, autorhythmic cells don't, is that contractile cells are unable to generate their own action potential, but autorhythmic cells can. And that's actually why they're called autorhythmic, because they can generate a rhythm of action potentials automatically, completely on their own. So these are kind of two cell types, and now we're going to dive into contractile cells and look at their anatomy on a more microscopic level and see how that anatomy dictates how they behave. So these are the cells that can generate force. These are the cells that just said have sarcomeres. So if we draw these out, I'm going to draw one contractile cell, shown here in yellow. A second one, its immediate neighbor. And what we're going to see is that they're connected by a few different structures. We have this one connection, and then I'm going to draw this second connection here in green, and I'll get to in a second what each of these structures actually are and what they do. So again, these are contractile cells, so they have sarcomeres just like we saw in skeletal muscle. They have actin there shown in white. They have myosin, the thick filament shown there in blue. They're the force generators. But what's unique about these contractile cells in the heart is that they have this structure called an intercalated disc. And this intercalated disc is composed of two units. One is the desmosome, and y'all might remember that the role of these is to coordinate the contraction or the force between one cell and its immediate neighbor. It really is just a physical structural connection between this cell and this cell. So if this contractile cell in the heart starts generating force, starts contracting that way, it's going to ensure, the desmosome is going to ensure that this cell starts being pulled that direction as well. And what we're going to see is that this allows for really good coordination between when one cell in the heart contracts, the other one begins to contract. Because we'll see that the heart, unlike skeletal muscle, needs to contract in a very coordinated way. The sequence has to be just right. The atria have to go first and the ventricles have to go second, always. These desmosomes are going to ensure that we kind of have that nice coordination in force. But we also have this other structure known as gap junctions, which is pretty much just an open protein that allows for charge or action potentials to spread from one cell to another. So for example, let's say that this contractile cell at the top starts having an action potential. It will stimulate to have an action potential. Through that gap junctions, we can spread that positive charge and generate a new action potential in the neighboring contractile cell. So what that ensures, again, is that we coordinate the activity from this cell with this cell. This cell starts generating force, it's going to start pulling this one in the same direction using the desmosome. This one generated an action potential, it's going to make sure that its immediate neighbors get stimulated right after it using this gap junction. So in the heart, all the muscle fibers are working with their neighbors to ensure that when they go, everybody around them goes next. So again, very, very coordinated stimulation and contraction process. All right, so again, what we're going to try to do is try to compare everything we learned about how skeletal muscles contract and apply this to how cardiac muscle contracts. So we're going to do a quick review of skeletal muscle contraction, and then we're going to use that as a basis for explaining how cardiac muscle contracts. So quick review. If we look back at our skeletal muscle contraction process, and we'll go over it kind of generally. There are some steps that we talked about, which I won't include here. Just general brief review. We had a somatic motor neuron coming out of the central nervous system. That somatic motor neuron was responsible for talking to a skeletal muscle fiber, which I've drawn terribly here, but shown there in orange. So the somatic motor neuron has an action potential that goes to axon terminal, triggering the release of acetylcholine in the synapse. That acetylcholine, we said, binds to acetylcholine receptors or nicotinic receptors. As a result of that, sodium goes through those acetylcholine receptors, making the muscle fiber more positive and triggering, ultimately, an action potential. So again, just review. And then we saw that once I have that action potential, that's what triggers the release of calcium and generates force. So we kind of have a sequence of 3 steps when generating skeletal muscle contraction. We have this first excitation in the motor neuron. This one is having its own action potential. Then we have excitation of the actual muscle cell. So kind of a second excitation. We just took this action potential and caused an action potential in the muscle. And then finally we have contraction or force generation. So we're going to see that in cardiac muscle, this sequence is exactly the same. We're going to have an initial excitation in a cell that is not generating force. We're going to have a subsequent excitation in a cell that is responsible for generating force. And once we get this, then we get contraction. So let's take this picture and try to compare it now to the scheme that happens in cardiac muscle. So in cardiac muscle, we're going to have that same excitation, contraction process, but the cells are going to look a little bit different. So instead of our motor neuron, we're going to have an autorhythmic cell. They're going to be the ones responsible for generating that first excitation. They're then going to be connected to a network of contractile cells shown here in orange, the ones that actually generate force. So I tried to color code them, the contractile with the skeletal. So the yellow ones produce the first excitation. We have the autorhythmic cells, which are functioning a lot like the motor neurons in skeletal muscle. We have the contractile cells, which are functioning just like skeletal muscle fibers to generate force. So the idea is if I have an action potential in autorhythmic cells, that positive charge can spread directly through gap junctions to neighboring contractile cells. So whereas before in skeletal muscle, that action potential was jumping to the muscle fiber using acetylcholine, now that action potential can jump directly using gap junctions. Now the contractile cell gets more positive and it generates an action potential as a result. Just like in skeletal muscle, that action potential will then generate force in contractile cells. So you have a very similar sequence. Excitation in a cell that does not generate force, just like before, excitation in a cell that does not generate force, that transfers to excitation or an action potential in a cell that does generate force, just like before, excitation in a cell that does generate force, and ultimately that excitation leads to contraction in that force generating cell, just like before. So a little bit different cell types, autorhythmic cells as opposed to somatic motor neurons, contractile cells as opposed to skeletal muscle fibers, but really they're serving the same purpose in both cases. And so what we're going to do now is dive a little bit more deeply into these different kinds of action potentials, the ones we're generating in the heart. Because what we're going to see is that the heart is, since it serves such a specific purpose, since we want it to behave in such a specific way, the action potential that we learned about in skeletal muscle fibers and somatic motor neurons is just not going to cut it. It just doesn't work for the heart, as we'll talk about in class and you'll work on problems. So what we need to do is actually have an action potential that looks a little bit different in autorhythmic cells. So let's dive into what that action potential looks like and explain why it needs to look the way it does. So this action potential in autorhythmic cells, this first excitation, we're going to see looks a little bit different than the action potential we've seen before. So we're going to draw that out real quick. You'll notice that one thing is that this action potential in autorhythmic cells is going to start with a resting state of around minus 60. Threshold for this action potential is around minus 40. And just like always though, we get to threshold using some sort of sodium influx. So we start getting more positive using sodium. Sodium comes in, makes the cell more positive, gets us to threshold. And we're actually going to call this what's known as the pacemaker potential. Usually when we talked about regular action potentials or skeletal muscle fibers, we would say a graded potential gets you to threshold. This pacemaker potential is just like a graded potential that we talked about before. Its job is to get you to threshold to trigger an action potential. But the reason it's called a pacemaker potential is because in this case, as we'll see in a few seconds, this graded potential is going to help you set the pace of the heart. And we'll see that in a second. Okay, so we get to threshold, we get to minus 40, and we'll see that at minus 40, we begin our action potential, but the difference here now is that this depolarization is caused by voltage-gated calcium channels. This is a unique feature, something we did not see in previous action potentials, where calcium is actually causing the depolarization. Just like in previous action potentials though, we repolarize using potassium, so voltage-gated potassium channels open and potassium leaves, making the cell more negative again. So there are some differences here compared to previous action potentials, but maybe nothing too different just yet. We got to threshold, we stimulated an action potential. One difference is that this depolarization is caused by calcium. But then we repolarize using potassium, which is pretty standard, so nothing looks too different, even though it looks a little bit different. The big difference, though, is what is about to happen next. So check this out. As soon as I get back to minus 60, we get this phenomenon that we have not seen as of yet. What happens when I get back to minus 60 is that there's this set of voltage-gated sodium channels that spontaneously open at minus 60. We have never ever seen a voltage-gated channel like this. Every single voltage-gated channel we have seen opens when the cell gets more positive. For example, this voltage-gated calcium channel, we had to make the cell more positive to get it to open. These voltage-gated potassium channels opened when we got really positive. But these autorhythmic cells have this very unique voltage-gated sodium channel that responds to the cell getting much more negative. And the reason that's so important is because as soon as we get back to minus 60, these voltage-gated sodium channels are going to open again. They are not going to rest when you get more negative. So this is a very unique channel that is activated by negative charge. And so what this ensures is that this autorhythmic cell will never rest. It'll always start another action potential. Because once you start one and you repolarize, once you get back to minus 60, this voltage-gated sodium channel is going to pop open again. You have another action potential, you repolarize, you get back to minus 60, and it is going to go again. And that's actually why we say that these cells have what's known as an unstable resting membrane potential. They are literally never at rest. And this diagram right here is exactly why your heart can beat when you don't think about it, why your heart can beat when you're asleep. Because once you start one action potential, you're going to get one right after, whether you're thinking about it or not. Once this cell repolarizes, it's going to start another action potential immediately after. So the reason we have this unique action potential, this one that can regenerate itself, is because we want autorhythmic cells to be able to automatically have a rhythm even if we're not thinking about generating contraction in the heart. They're spontaneously going to generate a rhythm for action potentials. And depending on how quickly they generate the action potential or how slowly, that's going to set the pace of the heart, the pace of excitation, and that's why we call this initial voltage-gated sodium opening the pacemaker potential. How quickly this happens was going to set the pace for contraction in the heart. So we have this unique action potential, spontaneously open at minus 60, and it'll generate another one in rhythm, one heartbeat, second heartbeat, and forever every single second of your life. All right, so we have kind of an understanding of what the role of these autorhythmic cells is. And so if we go back to kind of the anatomy of the heart and draw out these network of these autorhythmic cells, every single one of these points in this yellow tracing is an autorhythmic cell. Every single one of these cells in this network can generate its own action potential rhythmically. So if we look at the SA node, the beginning of this autorhythmic network, the SA node is a collection of autorhythmic cells, and each of these cells in this SA node can fire an action potential 70 times per minute, so 70 beats per minute. We also have this other structure, among others, known as the AV node, the atrioventricular node. And the cells in the AV node tend to fire action potentials a little bit more slowly, only 50 times per minute. We have these structures down here in the ventricles, known as the bundle branches and the Purkinje fibers. So you guys might remember from anatomy. And these can fire their own action potentials too, but they do it much more slowly, around 25 to 40 times per minute. So again, what it means that this SA node is firing at 70 times per minute is that it's doing this action potential 70 times per minute on its own rhythmically. But we'll notice that depending on which autorhythmic cell you are, whether you're here, here, or here, you can fire those action potentials more quickly if you're in the SA node. You can fire them more slowly if you're in the AV node. And you'll fire them even more slowly if you're in the bundle branches or in the Purkinje fibers. And that's why the SA node tends to be called the pacemaker of the heart, because it's the one that will generate the fastest rhythm. So once it fires, everything else is going to follow after it. It's the fastest rate and therefore sets the pace of the heart. So once these SA node autorhythmic cells fire through gap junctions, it's going to spread that signal through this entire network of autorhythmic cells, and everybody's going to follow that faster pace. All right, so far, if we go back to that sequence that we kind of have where we have to generate excitation and then another excitation to finally get contraction, we've gotten our excitation done, where the autorhythmic cells have fired to generate the excitation. We know that that signal should be able to spread by gap junctions to the contractile cells. And now what we're going to do is look at what this second excitation in the contractile cells look like. Essentially, we're going to look at what the action potential in the contractile cells should look like. So this action potential, unfortunately, is going to be a little bit different too. So this is going to be the third action potential we've seen. And you'll see that one difference already is that the resting state of these contractile cells is a little bit more negative, around minus 90. But just like always, we're going to start depolarizing this cell using sodium. But in this case, it is going to be brought to threshold by the action potentials generated in the autorhythmic cells. So it's going to spread by gap junctions into these cells and bring them to threshold. And just like always, like we saw in skeletal muscle fibers and neurons anyway, we're going to start the action potential using voltage-gated sodium channels. And so we get really, really positive due to all this sodium coming in. Then we get to some peak of depolarization, and we begin to repolarize just like we always do. and that has always been due to potassium channels. Voltage-gated potassium channels, potassium leaves, and we get a little bit more negative. So nothing too different compared to the neuron's action potential, where more negative than normal in these contractile cells. But voltage-gated sodium causes depolarization, voltage-gated potassium causes repolarization. But here's where the big difference comes in. In neurons, we usually just kept repolarizing and got really negative really quickly to get ready for another action potential. But in contractile cells, they do this weird thing. Well, at this point, after they've already opened voltage-gated potassium channels, after they have already inactivated sodium channels, so remember the inactive sodium channel will look like that, where the inactivation gate is closing this channel. After they've gone through all of this, they're going to have this weird phase where they'll open up voltage-gated calcium channels to allow calcium to come in. And you'll notice what happens is because calcium's coming in, the cell doesn't get more negative anymore. It actually stays really positive. So this is what's known as an extended depolarized state. So it's staying in a more positive state for an extended period of time. It's also known as delaying repolarization. It's a delay in you getting more negative again. And then eventually, once we get through that state and we get through this long extended depolarization, then we open up another set of potassium channels and finally repolarize. Kind of this second set of potassium channels that triggers repolarization. So really this action potential is not too different from the very first one we learned this semester, except for this weird section here where we opened up voltage-gated calcium channels and we got this plateau in the action potential. And so why is this plateau so important? And so we're going to go through each phase, and I'm just going to try to explain and recap exactly what's going on in each of these phases. During phase 1, voltage-gated sodium channels open, allowing sodium to come in. Phase 2, voltage-gated potassium channels open. Potassium goes out, making it more negative. And at this point, just like we saw back in neurons, the voltage-gated sodium channels are going to become inactivated. This little inactivation gate is going to close these channels up. And so the sodium channels should look like this during this phase, during the repolarization. During phase 3, these voltage-gated calcium channels open. So there's a delay in repolarization. We don't get negative as fast as we might. And so what this means is that the cell's going to stay more positive for longer. And because of that, this voltage-gated sodium channel is going to stay in this inactivated state. Because what we said back in the day is that for us to make this sodium channel go back to its original conformation, we need to make the cell more negative. But if we delay the process by which the cell gets more negative, this sodium channel is going to be stuck in this state for longer. It's not until stage 4 when we trigger voltage-gated potassium channels to open and the cell gets really negative really fast that we can get this voltage-gated sodium channel to reset to its original positioning. So at this star, finally, this sodium channel is going to look the way it did at the very beginning. The activation gate's going to be closed, and the inactivation gate is going to reset. So who cares? Whatever. Why is this important? Well, let's look at where the absolute refractory period starts and ends in this new action potential. We saw back in the day that the absolute refractory period begins when the voltage-gated sodium channel is open, so it begins right here. And it's not going to end until the sodium channels look like this. So if I start the absolute refractory period here, still going, still going, still going, still going, and because of this delayed positive state, these sodium channels are going to still look like this. So it's still going, still going, still going. It's not until we get all the way back down here that the absolute refractory period stops. So why is that so important? Why do we need a whole new action potential to do that? So I know what you're thinking. We had the action potential in the neuron, and the action potential in autorhythmic cells, and now we have to learn another action potential. Oh my God. Why? Why do we have to do that? Why is it necessary to know all of these action potentials? Well, what I'm going to try to convince you of is that this action potential, the one we just saw, just might save your life. So if we look at what happens during the course of tetanus, we're going to see that even in somebody who has been infected with the tetanus bacteria, somebody whose skeletal muscles are contracting at full force or spasming at full force, for some reason your heart doesn't do that. It is resistant to experiencing tetanus. And it's thanks to that action potential that we just saw. So for example, let's draw as a review what happens in skeletal muscle as a result of tetanus. So in skeletal muscle, we had this action potential from back in the day that looked just like this. That was kind of the first action potential we saw. And we saw that this action potential in skeletal muscle would lead to force generation. So I'm drawing that out here. The force goes up and then no more stimulation, so the force goes down. But in this action potential, the absolute refractory period goes from there to there. So theoretically, I could stimulate this muscle cell again starting right here. But this muscle cell, this skeletal muscle cell, is still not yet fully relaxed. All of its calcium is not back into the sarcoplasmic reticulum yet. So if I stimulate it there again, what we saw is that the force is just going to build up. So if I stimulate another action potential there in that same muscle cell, while it's not relaxed, the force is going to sum. It's going to build up, and if I keep doing that, build up, build up, build up, until eventually we get to tetanus and maximum force. And that's why we saw in the case of that baby that had tetanus, involuntary tetanus, all of the skeletal muscles seemed to be contracting at full force and spasming at full force, because we could stimulate them so frequently that that force would build up. But if your heart does this, if your heart experiences tetanus, it would just contract and stay that way, and it would cease pumping blood. You would die in a matter of seconds, minutes. So we need a way for the heart to not experience tetanus. And that's where this new action potential comes into play. So if we compare this process in cardiac muscle, this new action potential might save your life if you ever get infected by the tetanus bacteria. So if we draw out this new action potential, we saw that it looked a little bit different where it was much longer because of this calcium plateau. That meant that the absolute refractory period was much longer. So if I draw the force generated due to this excitation, this contraction, what you notice is that the force generated from this one action potential lasts the exact same amount of time as this really long action potential. Which is great, because if I draw out what the absolute refractory period where it starts and ends, the absolute refractory period starts right here and it ends right there. So if I stimulate this muscle once and it generates force, what it means is that I cannot stimulate this muscle again until this muscle is fully relaxed. In skeletal muscle, I could stimulate this muscle when it was really contracted again, and I could build up that force. Cardiac muscle is going to say, all right, I'll let you generate force once, but I'm not going again until I'm fully relaxed. It's just not going to happen, which is great because that makes sure that the cardiac muscle will never experience tetanus. It'll always contract, but then relax. Contract, and then relax. So no matter how many times I stimulate this muscle or try to stimulate it, it just simply cannot experience tetanus. So if I stimulate it again, it's going to look exactly the same like the first one. There's going to be no buildup in force, no buildup in calcium, and therefore no tetanus. So now let's go back to that sequence of events we had. We had that first excitation, which we saw was generated by the autorhythmic cells with that autorhythmic action potential. That will then spread to the contractile cells using gap junctions and cause them to have their own action potential, which looked a little bit different. This extended plateau, which prevented them from experiencing tetanus. So this is the myocardial cells, the ones that actually generate force. Now what we're going to do is look at what the contraction process in cardiac muscle looks like. So we've got an excitation. Great. We've gotten our second excitation in the actual contractile cells. Cool. But we don't have contraction yet. What does this contraction process in cardiac muscle look like? And so I'm actually going to have you guys draw out this process in class. But for now, what I'm going to do is review skeletal muscle contraction. And we're going to use that as a basis for how cardiac muscle contracts. So let's just quickly review how skeletal muscle contraction works. The key details, anyway. So as a reminder, we had an action potential in the cardiac contractile cells. That action potential would interact with this receptor we called DHP, voltage sensitive protein. It would not open or anything like that. It would just change shape. And the reason that was so important is because DHP was connected to a protein on the sarcoplasmic reticulum known as RYR, this calcium channel. So that's just physical structural connection between these two. So when the action potential travels down, changes the shape of DHP, it's going to open RYR, which allows calcium from the sarcoplasmic reticulum to exit into the sarcoplasm or the cytoplasm of this muscle cell. And as we saw, calcium is going to bind to troponin, get all that mess done, and then we're finally going to get contraction of the sarcomere. So I'm leaving out some steps here, but you get the gist. And we said that in skeletal muscle, to generate relaxation, when we don't have action potentials anymore, we want to relax. We need to get that calcium back into the sarcoplasmic reticulum to generate relaxation. And we can do that by using a primary active transporter known as calcium ATPase. That's going to pump calcium from low to high back into the SR to get us to relax. So this is kind of the general scheme that we saw for skeletal muscle. Generate contraction by releasing calcium from the SR, generate relaxation by pumping it back in. So once these action potentials stop, calcium ATPase is now going to do its thing and generate relaxation. So what we're going to see is that the contraction process in cardiac muscle is nearly identical, but there are three key differences, and I put a little star next to the points that are going to be a little bit different in cardiac contraction. Everything else exactly the same. Everything else. There's an SR, there's calcium, there's troponin, there's sarcomeres, we have calcium ATPase. But what you're going to see is something's different about DHP in cardiac contractile cells. Something is a little bit different about RYR. And then there's this weird protein up here on the surface of cardiac muscle that we don't have in skeletal muscle. So I'm going to list out those differences for you. And then in class, you're going to actually draw out what the process of cardiac muscle contraction is based on these differences. So the three differences between skeletal muscle contraction and cardiac muscle contraction. There are a lot of difference between these two muscle types, but just the difference in the contraction process. That was a sloppy line. I'll erase that and make it a little bit neater. So the main one of the differences is that in cardiac muscle, DHP actually opens in response to the action potential. So in response to that action potential in contractile cells, DHP actually opens, and we're going to see that that lets in calcium. Calcium that comes in through DHP, so calcium that comes in from the ECF, is going to bind to and open RYR. This is different in cardiac muscle. The last difference is that in cardiac muscle, the calcium also must be pumped out of the cell, not only back into the SR, but it must be pumped out. And we're going to use a secondary active transporter to make that happen. So this new secondary active transporter is a lot like SGLT, but instead of sending glucose, it's going to send calcium. It's going to send calcium out of the cell instead of bringing glucose into the cell. So what I want you guys maybe to try to do is to review SGLT and take these three differences in cardiac versus skeletal muscle contraction and try to draw out this picture, but for cardiac muscle. So take this picture of skeletal muscle contraction and use these differences to draw out what cardiac muscle contraction looks like. And so in class for the Monday, Wednesday sections, we're actually going to be using this video to answer a bunch of in-class questions. For the Thursday, Friday section, this video is review of what we talked about on Friday. And also intro to some of this contraction process. But for now, just check out this video, review these action potentials, these two new action potentials, this new contraction process, and this will intro our segment that now we're going to be talking about the heart contraction process, the cardiac cycle, and the cardiovascular system by first learning how the heart gets excited and how it contracts.